Yeah, and it's like
He's like every time he gets on the car.
Okay, let's go ahead and get started. I'm excited about today's lecture. I was up till way past midnight and up early in the morning getting this ready for you, and I'm excited to share it with you. Mirrors and curved mirrors and lenses can look intimidating until you see it, okay? And it's a lot like electric circuits that way, that, you know, once you see it, it just makes sense to you. And indeed, in Montana, I wouldn't teach this because I felt it was just so straightforward and easy that what I did for my pre-med students, and remember I only had 15, is before they went to take the MCAT, I would meet with them for a couple of nights and just go over optics. And after a couple of nights, they were just, oh, that's all. Yeah, it was that easy. And so that's why it isn't at the, when you go to the Montana YouTube site, there are no optics lectures there. Okay, that's because that wasn't part of our course up there. Before we get started, let's pray for some inspiration. Would someone be willing to open with prayer? Thank you, Jameson.
Dear Heavenly Father, we thank you for this opportunity that we have to come to physics and learn more about that world, and we're grateful for our families that we have and for the opportunity to study at BYU. And Father, help us to feel like spirit as we learn. And we're thankful for Professor Francis for his preparation, and his blessings that we can continue to grow and learn more about thee. We say these things in the name of thy Son, Jesus Christ. Amen.
Amen. Thank you. Okay, let's begin with a review. Last day at the end, we were talking about color. First of all, Clark Snellgrove is going to be teaching the first lecture on nuclear physics on Thursday. And he asked me to put up this slide with the reading assignment. Some of it's reading, some of it's video that you watch. And this is posted at Max, so you don't need to write that down. It's there at Max. Okay, let's quickly take attendance. Okay, now you can click. Okay, get your clicker points. Okay, that's all. Oh, we're here. Good. Okay. Last day, what we found was that white light was made up of all the different colors, but that for humans, all we really needed were 3 colors, because we had in our eyeballs 3 detectors, one that measured red light, one that measured green light, one measured blue light. And then our brain put it all together. And so with red and green, we could make yellow. With red and blue, we make magenta. With blue and green, we make cyan. And those 3 colors, yellow, magenta, and cyan, are the secondary colors of light, but they're the primary colors of pigments. And by pigments, we mean paint, ink, anything that absorbs the colors rather than adds the colors. Okay, now pigments work on the principle of color subtraction. They remove some of the color. And so the light we see is just the light that's left over, what reflects off the painted surface. These gels, they're called, are also considered to be subtractive. And so, for example, this is magenta. We said that when I look at that and I see that it's magenta color, the white light is hitting that, red, green, and blue, but it's only the red and blue that gets to my eye. That's what magenta is made of. And so I can think of magenta as a green sucker. It just sucks in the green and holds on to it. And if you notice the green in the middle of that rainbow up there, if I put this up there, the green goes away. If you look at the right, you still see the purple. Let me douse the lights here for a little bit. Okay, there, that's okay. So you see, I still have the blue and the red. And now if I take the cyan, remember that's blue and green, that's a red sucker. That takes the red and holds on to it. And so all I get left is the green and the blue. And then the yellow, of course, is made up of red and green. That's a blue sucker. That just holds on to the blue. And so you see that the blue end is missing there. Now, because this subtracts or takes away color, you can see that the cyan, magenta, and yellow are primary colors of pigments because they only remove one of the colors. Whereas if I put up a red filter, it's already gotten rid of the green and the blue. All I got left is red. So if I take this projector and put a red filter in front of it, and then a green filter in front of it, the red takes care of, gets rid of everything that's not red. Okay, and I've got a rainbow there that I don't want. Let's put that rainbow somewhere else. So I've gotten rid of the green and the blue there. And so now when I put a green filter in there, I get nothing because there was no green to go through there. And if I put, on the other hand, yellow, well, that's letting the green and the blue go through. And so if I put magenta in front of that, tell your neighbor what this is going to look like when I put magenta in front of the yellow. Okay. Remember, magenta is yellow is a blue sucker. It's going to absorb the blue. Magenta is a green sucker. It's going to absorb the green. All I've got left is red. Okay. And so you've got some homework that is dealing with color addition and subtraction. And there will also be problems like that on the exam. Let me turn off our bulbs so that they don't wear down. Okay. I didn't want to do that. Wanted to do that. Okay. Now, so yellow absorbs the blue, cyan absorbs the red, magenta absorbs the green. Now, magenta and yellow we just saw on the board, and that gave us red. We could have done cyan and magenta to get blue, yellow and cyan to get green. Now, the complementary colors are the ones that when you add them together as light, you get white. You get all the colors that mix to white. But when you add the complementary colors with pigments, you get black, you get the absence of all colors because they absorb all of the colors. Now I have this animation here and whoops, that's not what I meant to do. Okay, what you're meant to do is stare at this cyan square for 30 seconds. Just stare right at the square. And what that does, you remember you've got 3 cones, a red, green, and a blue. And when you're looking at the cyan, you're using your green and your blue cones. And for 30 seconds, you're just staring at that. And you're fatiguing those cones, the red and the green. And so after the 30 seconds, we're going to show some white light. And, you know, that's supposed to trigger all of your cones, red, green, and blue. But your red and green are tired. They've been staring at this little cyan square. And so they're just, but your red cones, they're raring to go. They're all set. And so suddenly when we put white light up there, you're going to see a red square where there's not a red square. Okay, you're just seeing things. We're going to make you see things that aren't there. Okay, so let's start this. Okay, stare at it, come on. Otherwise you don't get your money's worth. Get those green and blue cones really fatigued. Wear them right out. Now we're going to put white up there. Do you see it? And then they're going to put up a red square that's really there. Yeah. Okay. That was fun. Okay. You're still seeing the red square? Okay. So black is not a color, it's the absence of color, the absence of light. And white is the combination of all the colors. Now, this is the type of problem you had for your homework. You were asked, you know, if I put this color paint under this color light in a dark room, what is it going to look like? And if you try to just memorize all the combinations, you know, that's like trying to remember all 12 bones of the body. That's just too hard, okay? So what you want to do is always think of light as being made up of red, green, or blue. You know, which of those 3 do you have? And so if I shine white light on a magenta paint, well, magenta, that's a green sucker. That's going to hold on to the green and it's going to send out red and blue. And so that's going to appear magenta. That's T-Mobile, okay? My son works for them. He asked me to put up that commercial there, okay? Now, if I take that same magenta paint and instead I put it in a dark room and put cyan light on it, well, now I'm only giving it green and blue. I didn't give it any red. And again, magenta is a green sucker, and so it holds on to the green and it appears blue, okay? On the other hand, if I put yellow light on it, again, green and red, magenta holds on to the green, and that magenta paint looks red, See if your neighbor understands color, because this is where we change gears and go a different direction.
I think looking at like if it's yellow, then it will bounce spreading around. Fire, it's a bounce. The green one is yours, that's-
Okay. We're going to talk first about mirrors because they're a little bit easier to understand. And we're going to find that lenses act exactly the same as mirrors, exactly the same. So right here I have an example of a converging mirror, concave mirror it's sometimes called. I like converging. And with a converging mirror, we're going to find that sometimes it gives us an image that's right side up, and sometimes it gives us an image that's upside down. Now, Greg, what do you mean by an image? Well, that's the game. That's the game we're playing here, is find the image. I have a little device here, and it's just two curved mirrors with a hole in one of them. And if you look right down the middle of that hole, what you see is just a little die, okay? Now, all of the light that leaves that die comes off in all directions and bounces off the two mirrors that are in there, the two curved mirrors, back and forth, back and forth. And then it all comes together in what we call an image. What you see floating above that, let me see if I can. No, that's not the way to look at it. Okay. You see how it's just floating about right here? I'm looking at it here, and it looks like I could just grab it. And when I try to grab it, my fingers go right through it, but it looks exactly like the die. That's an image. All the light that left the die came back together, and now it's spreading out. Some of it's reaching my eye. If you were standing there, some of it would be reaching your eye. We'd all think, oh, the die's floating in air there. And that's the way they did the ghosts in the Haunted Mansion at Disneyland. You know, you were leaving the Haunted Mansion, and suddenly you look and there's ghosts in your cart with you. And it's like a little hologram of ghosts. Okay. So the image is the other me. And what we're going to find is that if I put my face close to this thing, it's a shaving mirror. And my head is right side up and so big that I can see every pore. It's disgusting, okay? But as soon as I get a little bit away, oh, first I get enormous, okay? And at that point, I'm passing through what's called the focal point. And then after that, I'm upside down, just like you're all upside down. And so you can see that this kind of mirror would be a terrible mirror to use on the side of your car, okay? Because the trucks that are coming up on you would constantly be flipping from upside down to right side up. Not helpful, not helpful, okay? So let's talk about how that image is formed. Well, first of all, some definitions. We make a curved mirror by just taking a sphere that has reflective material on the inside, and we just cut off a part of it. And so this would be the radius of curvature of the whole sphere that we started out with. And what we find is that there's a special point that's halfway from the mirror to that center of curvature. We call that the focal point. And we call it the focal point because every ray that comes in parallel to this axis. We call this the principal axis, the axis of symmetry, if you will. Every ray that comes in parallel to that axis passes through this point. And there's an infinite number of them, Now, those of you that have ever used one of those solar ovens, okay, it's just a concave or converging mirror. And it takes all the rays from the sun and brings them down to one point. And if you were a bad Cub Scout, you could use that to start fires, okay? Bad. Now, how do those rays from the sun all be parallel to each other? Well, think about it. All the rays that leave the sun and get all the way through all that space and hit your mirror, they're all going the same direction, are they not? Yeah, otherwise they would have ended up on Mars. Okay, so now we use this idea to find our image, because we can also run time backwards. Any ray that goes through this focal point is going to hit my mirror and bounce off of it parallel to that axis of symmetry, the principal axis, okay? And it doesn't matter which ray I'm looking at, they're all going to bounce off parallel. Okay, so let's find an image. We call this the object because it's really there. I can pick it up, I can, I can find its mass, it's real. If I look at all the light that leaves the tip of that arrow, and it goes in all directions, but I'm just going to look at a few of the rays. There's an infinite number and they go in all directions, but I'm going to look at this first ray that comes in parallel to my principal axis. And I know where that ray is going to go. It's going to go right through the focal point. That's my first ray. My second ray, I'm going to send right through that focal point, and I know where it's going to go when it bounces. It's going to come off parallel to the principal axis. So far, so good. Now, all of the rays that leave that point, hit the mirror, are going to all come back together right there. All of them. I just used 2 to find the location. But every single ray that leaves that point up there, hits the mirror, has to go through that point, because that's where we formed the image. Now, 2 rays is enough to tell you where that image is. But it's nice to have some confidence. When you get into an exam, you want to be sure you got the right answer, right? Okay. So let's look at a third ray. I know that if I send a ray right into the center of that mirror, that by symmetry, it's going to bounce off at the same angle that it came in. Does that make sense? Okay. And so that's why I put this upside down object there. That's not really there. That's not real. I'm just doing that so that I know I didn't want to use a protractor to make this angle equal to that angle. So I just flipped that upside down and use that to make the angle. Okay. Now, I even can get a fourth one. And the fourth one is, if I take a ray and put it through the center of curvature, that's guaranteed to hit that mirror at 90 degrees. And that's going to bounce right back. And so now all 4 of those rays go through that point right there. Okay. And indeed, a ray that hits here is going to go through that point. A ray that hits here is going to go through that point. A ray that hits here is going to go through that point. All of the rays that leave this point come back together there. Questions on that? Okay. So here's a summary slide. Rays 1 and 2 are having to do with that focal point. If it comes in parallel, it goes through the focal point. If it goes through the focal point, it goes off parallel. And that's really all you need to find the image location. The other two are gravy. Ray 3 is just hitting at the symmetry point, equal and opposite angles, coming in and coming out. And ray 4 is the one that goes through the center of curvature and bounces straight back. See if your neighbor understands what we just did to find that image.
I remember.
Okay. Now, you'll notice that the image is not the same size as the object. The object is real, but the image is just where the light appears to be coming from. If I put my eye down here, that light that comes together there is spreading out in all directions, and some of it's going to hit my eyeball, and it's going to look like there's an upside down arrow there. We call that a real image because there really truly is light there. Okay, just like the image of this dye that was floating in air, that was where all the light came back together and was now spreading out, some of it coming to my eye. There's really light there. Now, how do I find how big that image is? We call that the magnification. How big is the image compared to the real deal? Well, we find that with some similar triangles. And this is where ray number 3 comes in handy. It comes in, bounces at the principal axis, and comes off at exactly the same angle it came in. And I know that when two triangles have the same angles, they're similar to each other, which means that their sides are proportional. And so that means that if I want to know the ratio of the height of the image, that's what this is, the height of the image, the ratio of that to the height of the object, okay, that's going to be the magnification. Well, by similar triangles, that's just going to be equal to the distance from the mirror to the image, that's DI. You thought DI was a place to get used clothes. No, that's the image distance, okay? And that we divide by DO, which is the distance out to the object. Now let's talk about this minus sign. That's just put there by convention to say that if DI is positive, and that's what you get for a real image, then I'm going to get a negative magnification. Okay, it looks like this is about a third of that distance. So my magnification here would be negative 1/3. The third means it's 1/3 as high. The negative means it's inverted. It's upside down. And a real image will always be inverted. Always be inverted. Okay. Now we're going to find all sorts of minus signs. We're going to find minus signs galore. And I'm teaching it right now the way it's been taught to everyone since forever. Okay. With all the minus signs and all the conventions and everything. And then for the last half hour, I'm going to teach you another way, a better way, a way that is only found in our textbook. And the optometrists use it as well. Okay. So finding images for a concave mirror. Let's start with an object that's far away. Again, we're just practicing. We first of all take ray 1 that comes in parallel to the principal axis and goes through the focal point. And then we take ray 2 that goes through the focal point and comes off parallel. And where they cross, that's got to be where all the light that leaves that top of the arrow ends up. And so that's going to be the tip of my image, will be right there. Okay? And so what we see is that the image is smaller than the object, it's inverted, and it's near F. And indeed, if I get this object further and further away, my image gets closer and closer to the focal point. Does that make sense? Well, yeah, because light that's coming from the sun, from infinitely far away, infinite, coming in parallel, all of the light, that's going to all focus down at the focal point, right? So the further I get away from that mirror, the closer my image is going to get to the focal point. Okay. And it's a real image because the light's really there. Now, if I wanted to see that, I would have to be looking in this direction because those rays have bounced and they're coming back. If the object were in infinity, the image would be at the focal point, but it would have 0 size. And so that's not really meaningful. Now, if I bring it in closer to this center of curvature, and I do those 2 rays, what I get is that my image is a little bit further away from the focal point and a little bit bigger. Okay? It's still a real image. I can still see it there. Now, I just crossed a boundary. I like to think of this as 3 different regions. I call this region 1, that's closer to the mirror than the focal point. I call this region 2, where you're between the focal point and the center of curvature, which is twice the focal point. And this I call region 3. And you see that whenever we have an object in region 3, our image is in region 2. Well, now if I put my object in region 2, what I find when I use those 2 principal rays is that my image is in region 3. And it's bigger than the object. I have something that's magnified, but it's still upside down. It's still a real image. Now, where would you have to put your eye to see that image? And this is something you're going to have to do in the tutorial homework. Okay? So what you need to do is remember that all of the rays that leave that tip are going to, if I just want to see the image of the tip there, I would take all the rays that leave the tip and I would send them through that, bounce off the mirror and go through the image location. So I would go to this end of the mirror and I would go to this end of the mirror and see where they bounce off. And then I could put my eyeball anywhere between those 2 lines and see the tip of that arrow. If I did the same thing for the bottom of the arrow, maybe I do that in a different color light, different color lines. Where those 2 overlap, I could see the whole arrow. Okay, see if your neighbor followed that. You're going to have to do a homework problem dealing with that. Okay, does everyone see why I chose these rays? There's an infinite number of rays that leave the top of that object and go in all directions. But it's only the rays that hit this mirror that come together right there. And all the rays that hit that mirror have to end up between these two lines, because these are the extremes. These are the rays that hit the top edge of the mirror and the bottom edge of the mirror. So if I pick any other place where it bounces, it's got to be somewhere in between those two lines. And so I would be able to see the image there. Questions? Yes, sir.
How do you decide what angle, like,
What's that?
how do you decide what angle to make it bounce off? Should they both go?
Oh, yeah, I didn't use a protractor at all. I just knew that all of the rays that bounce off that mirror have to come together right at that point right there. So I took it to wherever I wanted it, and then I just said, where's it gonna go from here? Since all the rays end up there, so does this one. Okay? Yes, Jameson.
At the point of intersection, is that the clearest point that we'll see the arrow?
Yes, and that's the point where I could actually put a white piece of paper and I would get a projection, just like on a projector screen, of that arrow right there. Okay, that's where it would be focused. If I would put my piece of paper here, I would still see a blur of the arrow, but it would be out of focus because some of the light that left the tip would end up here and some would end up there, and it would be fuzzy. Okay. Now, what if I put that object right at the focal point? Well, you know what's going to happen. All of the rays that leave are going to go out to infinity, and it's going to be really, really large, but it doesn't make much sense. And that's what happened when I put my face right at the focal point. It just got bigger and bigger until suddenly it just became, well, scary. Okay, scary. Now, here's where it looks like a shaving mirror. If you get that object closer to the mirror than the focal point, now when I look at the principal rays, my first principal ray appears to be coming from the focal point, okay? A ray that left the focal point, went through here, would bounce off parallel. And then I send one in parallel and it goes through the focal point. Now, those two rays are leaving in such a way that they're never going to cross. They're diverging, okay? And so what I do is I look for where they appear to be coming from. I look behind the mirror. And if I follow this ray back and I follow this ray back, they both appear to be coming from right there. And so that's where my image is. And indeed, every ray that bounces off this mirror is now going to appear like it's coming from that point right there. And so we would say that the image is upright. That's what makes it easy to shave, is because my face is not standing upside down. It's bigger than my real face. Again, that's what helps make it easy to shave, because I can see all the little stubble. And we call that a virtual image. Not because it's virtuous and of good report and praiseworthy, but because it's virtually an image. It's as if the light were coming from there. But in truth, this mirror was mounted on a wall, and behind the wall, there was dark and spiders. There's no light back here, but it appears like light is coming from back there. Remember, all the images from a plane mirror were virtual. Okay, now if I look into the mirror, I will be able to see that virtual image. Okay, the closer I get to that mirror, the closer the mirror looks like a plane mirror. Because I'm right there at the center where it's fairly flat. And so what I find is that my image is almost like the image I would get for a plane mirror. It's a little bit bigger, but not much, and it's right side up, okay? So this is getting very much like the flat mirror case. The image is slightly larger than the object, upright, nearly the same distance behind the mirror. It's also a virtual image. Okay. Now, it turns out that if you would like, you can solve all of these problems mathematically without drawing the rays, with what we call the lens equation. And that lens equation says that 1 over the distance to the object plus 1 over the distance to the image is equal to 1 over the focal length. And then we have, we've already seen this equation, the magnification equation, and that's just the height of the image divided by the height of the object, depends on how far they are away from the mirror. The minus sign just is convention to tell us if it's a real image, it's going to be upside down. If it's a virtual image, it will be right side up. Now, the minus signs are important in this case until I teach you a better way. Now, let's look at the 3 regions that I was talking about. I'm going to show the 3 regions, and I'm going to put the object in a solid color and the image in kind of a transparent color. And these are my 3 regions, region 1, region 2, and region 3. When my object is in region 3, my image is in region 2. When my object is in region 2, my image is in region 3. They play off each other. 2 and 3 play off each other. But when my object is in region 1, too close to the mirror, then I get an image on the other side of the mirror, and it's virtual. Okay, that's the summary. Okay. And then if you get closer to the mirror, it starts looking like a flat mirror. Now, I spent some time on mirrors because lenses are exactly the same. Exactly the same. You just fold along the dotted line, okay? And you get exactly the same thing. And I'll show you that in just a moment. Let's talk about convex mirrors, the ones that curve out. Okay, those are the type that you put on the side of your car. And the reason for that is that they are simple. They are brutally simple compared to the concave or converging mirrors. These diverging mirrors only have one region. Everything you put in front of that mirror is going to give you the same thing, okay? Anything you put in front of the mirror is going to give you a virtual image that's right side up. Thank goodness, because you want the cars in your mirror to be right side up, okay? So if I bring in ray 1 parallel to the axis of symmetry, it bounces out in such a way that it diverges, but it looks like the ray is coming from the focal point on the other side of the mirror. And we say that this mirror has a negative focal length. F is negative for a diverging mirror or a convex mirror, we call it. Okay. If we bring in ray 2, it appears like it's going through the focal point, but when it hits the mirror, it comes off parallel. And where these two intersect, that's where I have my image. And so I'm always going to get an image that is smaller than the object. It's right side up, and it's virtual, meaning there's no light back here. It just appears like light is coming from there. Okay. And if I get closer to the mirror, oh, and we still have this equation for the magnification. That's universal. for a lens, it's exactly the same. We just fold it back. Let me go back here. As I get this closer, I'm going to get something that if I get this further away, I'm going to get this closer to the focal point. So if I get this closer, this is going to get closer. Okay. Let's talk about lenses. Again, we have two flavors. We call this a converging lens in that it brings all the parallel light coming from the sun and it focuses it down to a point, a focal point. And then we have a diverging lens, which takes all the parallel light and spreads it as if all that light were coming from a focal point on the backside. And we call this a positive lens, and we call this a negative lens. Okay? Now, how does a lens work? Well, we talked about that last Thursday. When light comes from a fast medium like air and goes into a slow medium like glass, it bends towards a normal. And then when it goes from the slow medium like glass into the fast medium like air, it bends away from the normal. And those two bends, one going into the glass, one going out, is what causes the light to focus down to the focal point. Now, what we do when we're doing our principal rays is we don't bother with all the details right there. We just take a symmetry axis down the middle of the lens and let all of the bending happen there, even though that's not what happens in real life. In real life, it bends at the boundaries. Now, again, if I bring in parallel light, let's do that. I have parallel light here, and going to turn off the lights. Okay, and so if I take, and you can play with this in the hallway right out here with better lasers, but you see it takes all those parallel beams and focuses it down to a focal point right there. Whereas the diverging lens takes all of those rays and spreads them out as if they were coming from back here. Okay, and what we're going to find next Tuesday is that it's very, very easy to add lenses, especially with the method in our textbook. If this one is spreading the rays and this one is bringing the rays together, when I put them, you know, they just both happen to have the same focal distance. We call that the same power, one positive and one negative. And you see it brings those rays back parallel. Okay, the one undoes the other. Okay, now. So if I look at the diverging lens, again, I have these two refractions at the two interfaces, but now those two refractions are bending the light away from each other. So let's first of all look at the positive lens, the converging lens, and find the image. Well, the first ray we put down there is parallel to the principal axis. I make the bend right in the middle just to simplify things, but it really happens at the surfaces. This ray that comes in parallel goes through the focal point. Likewise, if I send a ray through this focal point on the the near side, it comes out going parallel. And where those two cross is where my image is going to be. The image of this, the top of this object. Now, I've got some gravy here, and that's a ray that goes through the symmetry axis, doesn't bend, okay? It bends a little bit and then unbends on the other side, but if we take a thin lens, we find that it's insignificant. And so I can just draw, I can use my ruler and just go right through the center. And if I take those three rays, I'm sure that that's what my image is going to look like. Now, if I do the concave lens, what I do is this time I come in parallel and it spreads away from the axis, but it looks like it's coming from the near focal point. The other ray, I send as if it were going to the far focal point, and when it gets to the lens, it bends away, so it comes off parallel. And then my third one again is just the symmetry axis. And where these three cross or appear to cross is where the image is. And just like with mirrors, the diverging flavor is the simple flavor. It's only got one case, and that is I'm always going to have a virtual image, and I'm always going to have the image right side up. And it's going to be on the same side as the object. Check on your neighbor. See that your neighbor's on the bus here. Okay. Now, the next 10 slides, I just put in here so that you would have them. They're in your, the copy of the lecture that I put at Matt's, and this is just for reference. You can just look. I put an object in front of a converging lens, and that's where the image location is. And you see that when I'm in region 3, my image is in region 2 over here. And the closer I get to that center of curvature, the closer, this is twice the focal length. The closer this gets to twice the focal length. And then we cross over. This is now in region 2 on this side, and the image is in region 3 on that side. And the closer I get to this focal point, the bigger the image gets until it goes to infinity as I reach the focal point. And when I cross the boundary and get too close to that lens, well, now I can't focus that light fast enough. And so the rays come off, never reaching each other. And so they appear to be coming from behind the lens. And now I have a virtual image. And the closer I get to the lens, the smaller that virtual image gets, but it's always going to be bigger than the object. Okay, again, the diverging lens is just brutally simple. I always get an image that is right side up in virtual, and the closer I get to the lens, the bigger it gets. Okay, one more time, we're using our clicker just to make sure that you're still here. Okay, last call. Is that all of us? Good. Okay. Again, all of these problems, every single case can be handled, whether it's a lens or whether it's a mirror, with the lens equation. And the magnification, again, whether it's a mirror or a lens, can be found with the magnification equation. But here's the caveat. I've got all of these conventions for minus signs. The object distance is always positive if you're on the light side of the lens or mirror, the side where the light originates. Well, when would that not be the case, Greg? You always start on the light side of the mirror and the light side of the lens, because the object's where the light starts. Well, it turns out that when we add two lenses together, the image of one lens serves as the object of the next lens. And where that object ends up relative to the next lens determines whether it's positive or negative. If you do it this way, the way everyone else in the world does it. Hang on. The distance to the image is going to be positive if it's real, negative if it's a virtual image. The magnification is going to be positive if the image is upright, negative if it's inverted. The focal length is always positive for a converging lens or mirror, and it's negative for a diverging. Lots of minus signs, lots of minus signs. Indeed, here's a table that gives you all the different signs. Use it if you want. Memorize it if you want. And yet, in 1 Corinthians 12:31, it says, "But covet earnestly the best gifts, and yet shew I unto you a more excellent way." Let me show you a more excellent way. This is the way we present it in our textbook. And if you did your reading, you've already seen it. We use Huygens' principle. And Huygens taught us that you can ignore the past history of a wave. If you just consider a particular slice of the wave right at noon, at some particular time, right at noon, and you treat each part of that slice, in this case, that would be a crest of the wave. If I treat each part of that as a new source that sends out little Huygens, we call them Huygens wavelets, little circular wavelets like a ripple on a pond. And then you add those wavelets all up together, and if you wait long enough, one period of the wave, you get the next wavefront, the next wavefront. Okay? Maybe you're not thinking that's so useful, but it is. If I look on a two-dimensional surface, like the surface of a pond, if I throw a pebble in there, it sends out ripples in all directions that are circles. Now I can think of each of those ripples as a source of an infinite number of these little Huygens wavelets that are all going out from their location. And then a little bit later, those wavelets combine to give me the next wavefront. And so the wavefronts would be nested circles going out. In 3 dimensions, they would be nested spheres inside of each other like Russian dolls. And the rays that are always perpendicular to the wavefronts would be radially outward in every direction. Okay? Now, where am I going with this? We're almost there. We're going to do something very different than the standard textbook. Instead of talking about distances from the mirror or distances from the lens in meters, we're going to talk about curvature of the wavefront. And the curvature of the wavefront is given the symbol capital K for curvature. Curvature, okay? Now, it's just 1 over r. Now, think about that. If I have just a point, well, that's going to be r equals 0, and that's going to be k is equal to 1/0 or infinity. If I have a plane wave that are just straight, well, that's going to be radius equal infinity, and that's going to be curvature equals 0. Okay? Now, so a small radius gives us large curvature, and a large radius gives us small curvature. Now, what are the units of curvature? Anyone know? Anyone been to the eye doctor lately? The optometrist? Diopters. Diopters. Yeah, when you get your contact lenses, they have a certain diopter reading, a power, and that's either positive or negative. If it's positive, you've got a converging lens. If it's negative, you've got a diverging lens. But the power is measured in diopters. And I'm here to tell you, optometrists know optics, okay? And if they do it this way, this must be the easiest way. This must be the easiest way. So we only need one minus sign if we go this route. Only one. Only one. And that is whenever we have a wave that is diverging, whenever the wave is diverging, getting bigger, we say that has negative curvature. And by convention, we take the curvature to be minus 1/r. If that wave is converging, coming together to a point, we by definition call that positive curvature, and we say it's positive 1 the radius. Okay, and that's the only minus sign we need. That's it. Anything that is diverging is negative. Anything that is converging is positive. And from now on, for the rest of the lecture, whenever I've got negative curvature, I'm going to do that in red. Whenever I have positive curvature, I'm going to do that in blue. Okay? Now, let's first of all take a look at that case where I have an object far away from a converging lens. Well, if I start with a point, say a little flashlight bulb, the light's going to go out from that diverging, spreading out. And so that's going to be negative curvature. And I don't care what the curvature is right here. I care what the curvature is right there where it interacts with the lens. Okay? And that's going to be negative because it's spreading out. Now, what that lens does to that wave front is it slows down the middle and it doesn't slow down the sides. Because that wave, that light, slows down in the glass, and it has to go through a lot of glass here, it's fat in the middle, it slows down the middle of this wave front and lets the edges get ahead. And as a result, I end up with a positive curvature on the other side, a converging lens. It takes light that was spreading out and brings it together, okay? Now, the power, that's what the P stands for, the power of the lens, I can very easily calculate. Okay, first of all, I'm bringing in a negative curvature. I've got a positive lens, and that's going to change the curvature to positive. Now, this is how I find the power of the lens. I know if I send in parallel rays, which would have 0 curvature, I'm starting with nothing. That lens takes that 0 and focuses it all down on that focal point right there. And so 0 plus the power of the lens gives me this curvature as it leaves the lens, which is positive 1 the focal length, because all of that's going to go right there. Check on your neighbor, see if your neighbor's still with me. Questions?
Power.
Okay. Now. Look at this. We found with a curved mirror or with a converging mirror or a converging lens, if we got too close, we got a virtual image, okay? And it was right side up. Well, how close did we have to get? Well, we had to get closer than the focal length. And let's see if we understand why. If I'm closer than the focal length, I have a really, really, really big curvature. And it's negative. And it's so big that the power of my lens is not big enough to turn it positive. This is really big negative, and this is only so much positive, okay? And I'm gonna end up with something that's still negative. It's still gonna be spreading when it gets to the other side of the lens. This is trying to make it converging. It's slowing down the middle a little bit, but not enough, okay? And if I start with a distance less than the focal length, then this curvature is going to be bigger than the power of the lens, okay? Now let's look at a diverging lens. If I want to know the power of a diverging lens, again, I give it zero curvature. I give it a plane wave, parallel raised to the axis. And then that lens takes what's given to it, zero, and adds its power. And this time it slows down the edges, because that's thick, and it lets the middle go fast. And that's what causes it to be negative curvature on the other side. And so the power of a diverging lens is going to be negative 1 over the focal length. And that's why we call it a negative lens, a negative lens. Now, let's look at that wave, that lens equation, the mirror equation, okay? 1 over the distance to the object plus 1 over the distance to the image is equal to 1 over the focal length. And when you use this equation, the way most people do, you have to remember, when is F positive, when is it negative, when is D initial positive, when is it negative, when is DO positive, when is it negative. It's hard. It's hard. But if I just change things around, I'm going to take this 1 over DO, the object, over to the other side, and I get this minus sign. Now, what that minus sign means in my way of thinking is that this is the initial curvature. And because I'm starting and spreading out from my source, that's always going to be negative, okay? And so I put it over on this side of the equal sign so that it's negative, because it's always spreading out, okay? And then this power, well, that's what it was, what we just talked about. For a converging lens, it's positive. For a diverging lens, it's negative. And then I can figure out whether this is positive or negative. Now, this is not the form that we saw before. We saw it in this form. But I think you can see that I just took the right side and shoved it over here. And I took the left side and shoved it over there. What you start with in the morning, plus how the lens changes it, is what you end up with on the other side of the lens. Do a buddy check. Check your neighbor. No child left behind.
So I didn't have to.
Okay. In the remaining 5 minutes, let's look at an example. If I put an arrowhead that's 1 centimeter tall, and this example is right out of our textbook. If I put it 33 centimeters in front of a converging lens, and that converging lens has a power of 2. 2 what? 2 diopters, or 2 meters to the -1 power. Okay, 2 diopters. Well, what is the focal length of that lens? If its power is 2 diopters, what's the focal length of it? Tell your neighbor real quick. Who knows? Raise your hand. Yes. 0.5 meters, so it'd be 50 centimeters. Yeah. So what you see is that this is closer to the lens than the focal length. The focal length is 50 centimeters, and it's 33 centimeters from the lens. The power is 1 over the focal length. And so if I take 1 over 2, that's half, and it's in meters. Okay. Now, if I want the initial curvature when it reaches this lens, I take this distance, because the light that starts here spreads out over a distance of 33 centimeters. I have to make that into meters, and what I get is a -3 diopters. -3 diopters. Now, what does the lens do to it? Well, it takes the -3 that I give it, and it adds the power of the lens. -3 diopters plus 2 diopters gives me -1 diopters. Okay. Now, the fact that that's negative means that it's going to be a virtual diverging wavefront. Okay, so that immediately, I don't need to keep track of, is it on this side of the lens or that side of the lens? If it's got negative curvature, it's spreading out and it's virtual. Okay. So because that's a -1, that means that it's going to be 1 meter, 1 over 1 really, away from the lens, and it's going to be a virtual image, so it's going to be right side up, and I can find the height of it by using the magnification. If I take the distance to the image divided by the distance to the object, that's 1 over 0.33, and that gives me 3. It's a magnification of 3. And so if the object was 1 centimeter high, the image is 3 centimeters high. That's the way you work your homework. And the tutorial is already posted at YouTube. And so let's stop here, folks. It's going to be fun. We'll practice on Tuesday. Thank you all.